Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 8, Why Stay with Whole Numbers. Opening exercise. The sequence of perfect squares is 1. 1 times 1 is 1. 4. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25, and so on. Earned its name because the ancient Greeks realized these quantities could be arranged to form square shapes. So, first, 1, second, third, fourth, fifth. 5 by 5 square, 4 by 4 square, 3 by 3 square, 2 by 2 square. If S of n denotes the nth square number, what is a formula for S of n? So you'd say the formula for S of n equals n squared. Okay, so proving whether or not 169 is a perfect square would be really complex. You probably won't get into proving things like this till college, a formal proof. And you'd probably prove it by proving something is not a perfect square, not whether it is. So let's just look at it from this point of view and think about what we could do to keep increasing. So 5 times 5 is 25, and 6 times 6 is 36, and 7 times 7, and so on and so on. And I can say that 169 is a perfect square because 13 by 13 arrangement of dots would equal 169. Therefore, 13 squared equals 169. Okay? 2 says prove whether or not 200 is a perfect square. Okay, well, how can we prove that 200 is a perfect square? If 200 is a perfect square, then there's a positive integer a that we don't know, such that a squared equals 200. Okay, so I could say, well, let a squared equal 200. And then we need to know what our perfect squares are. 14 squared equals 196. So it's got to be more than 14. So then I'd go on to 15. 15 squared equals 225. So I now see that since 200 is between 196 and 225, so I'll do this. 100 and, wow, that's a weird 9. 196, and I'll put 225 here. And hopefully you all agree that 200 falls in between 196 and 225. Okay? So 200 is greater than 196 and less than 225. So 14 squared is less than 200, and 200 is less than 15 squared. Therefore, the square root of 200, in this case a, so this is my a squared. Therefore, a squared equals something between 14 and 15. I shouldn't say equals. A squared is between 14 and 15. So a is between 14 and 15. So therefore it's not an integer. So 200 is not a perfect square. So that's the easiest way to prove something is not a perfect square, by finding the perfect square on either side of it and proving that they're consecutive integers and there can't be another integer in between them. Therefore, not a perfect square. If S of n equals 225, then what is n? Okay, so what they mean by this is, since our S of n equals n squared, that's the formula we're using. So if I have S of n equals 225, actually let me put the formula here, equals n squared, and S of n equals 225, then I can then say the transitive, if a equals b and b equals c, then A equals C. So, in other words, if n squared equals s of n and s of n equals 225, we can then conclude that n squared equals 225. And to solve for n, I can take the square root of both sides, and the square root of n squared is n, and the square root of 225 is 15. Okay, so I'm going to keep doing this. I'm going to say, which term is the number 400? So going back here, what I'm using is this formula right here, and then taking that formula and setting it equal to the number they're giving us. So this is which term is the number 400, the sequence of a perfect square, in the sequence of perfect squares. So in other words, they're saying s of 400 equals what? Okay, well, if s of n equals n squared, okay, so I don't have this right here. This should be my s of n. So let me just fix that. Equals 400. So that's saying which term is the number 400, the sequence of perfect squares. So what number squared is 400 is what this question's asking. So s of n equals 400 and s of n equals n squared. Since they're both equal to s of n, they're equal to each other. So then I could say n squared equals 400. And then I take the square root of both sides and get my answer. So instead of arranging dots into squares, suppose we extend our thinking to consider squares of side length x centimeters. Create a formula for the area a of x centimeters squared for a square of side length x centimeters. A of x would equal what? Okay, all we're doing here is changing the number inside here from n to x, so it's just simply going to be this formula here. And instead of s of n, it's a of x, and that's going to equal what's in the parentheses squared. Use the formula to determine the area of squares with side lengths of 3 centimeters, 10.5 centimeters, and pi centimeters. So I would say a of x equals x squared. A of 3 equals 3 squared. So therefore a of 3 equals 9. And since they were centimeters, the area is now centimeters squared. So a of x equals x squared. Forgot my equal sign. A of 10.5 equals 10.5 squared. So a of 10.5 equals, okay, I have my calculator here, so all I have to do is 10.5 squared, enter. I could have also done it manually, but that's fine. 110.25. Okay, centimeters squared. And then finally, let's move all this. And then finally, we're going to do pi. So I'm going to write my formula. A of x equals x squared. In this case, my x is pi. So a of pi equals pi squared. That's it. We're done. Centimeters squared. All right, number 7. What does a of 0 mean? Well, if we have the formula, a of x equals x squared, a of 0 means 0 squared, which means 0 times 0. Okay, you can't have a square measuring 0 sides, so it has no meaning, if that makes sense. Number 8, what does a of negative 10 and a of square root of 2 mean? Okay, this is kind of lengthy, so I'll just bring in a typed answer. Okay, so in this situation, a of negative 10 has no physical meaning since a square cannot have sides whose measures is negative. In our scenario here, we're talking about square side lengths. A of square root of 2 does have meaning, although it would be impossible to measure that side length physically with a ruler because it's an irrational number. The only way for the input to be negative is if we redefine what the input value represents. Perhaps we just want to find the square of a number, not relate it to geometric figures at all. Then you can find that negative 10 squared, because it would be negative times a negative, which is positive, and 10 times 10 is 100. And when you take the square root of 2 and you square it, you get 2. Okay? All right, so anyhow. Now the triangular numbers are the numbers that arise from arranging dots into triangular figures as shown. What is the 100th triangular number? Okay, so hopefully you work this on your own, but what I would do is count rows by columns, if you will. So here, this would just be 1, and this would be 2, and this would have 1, so it's 2 plus 1. And this is 3, and this has 2 in this row, and this has 1, so that'd be 3 plus 2 plus 1. And this is 4, and this is 3, and 2, and 1. You get the idea? So this is 4 plus 3 plus 2 plus 1. And this is 5, and this is 4, and this is 3, and this is 2, and this is 1. So this is 5 plus 4 plus 3 plus 2 plus 1. So this one comes out to be 3. This one comes out to be 6. This one is 4, 5, 6, 7, 8, 9, 10. And this one is 5 plus 4 is 9, 10, 11, 12, 13, 14, and one more is 15. So what are we doing here? Adding 3, then adding 4, then adding 5. Obviously, that's the bottom row to the last. So we have to come up with a formula. Consider using T for triangle and N for number of dots per row. So in this triangle, it'd be T of N equals 2 plus 1, which is 3, and T of N would be 3 plus 2 plus 1, which is 6, and so on and so on. So if we do this, then we can get something like, let's see, some number, N, and then we're going to add that to one less than that. So we're talking the bottom row. So in this case, it'd be 1 plus 1 minus 1, or 0. And in this one, it'd be 2 plus 2 minus 1, which is 1. But then if I go out another term, it'd be N. No, that's right. N minus 2 plus N minus 3, and so on and so on. All the way out to N. So in this problem here, N is 5, N minus 1 is 4, N minus 2 is 3, 5 minus 2 is 3, 5 minus 3 is 2, 5 minus 4 is 1. So we would have stopped right here for this triangle. So we're leading up to something here. This could also be written as T of N equals 1 plus 2 plus 3 plus 1 plus 2 plus 3 plus 4 plus ... all the way out to N. So we could start at the top. 1 plus 2 plus 3 plus 4 plus however many there are in the bottom row. Okay, adding these together now, if I add these together, okay, T of N, that'd be 2 T of N's equals N plus 1 plus N minus 1 plus 2, which is N plus 1. I'll put these in parentheses too. So that's, here, let's do it in colors. Let's color code this. So my first term here, N plus 1. plus, let me change colors. Now I'm adding this. N minus 1 plus 2 is n plus 1. And then when I add n minus 2 plus 3, well, 3 minus 2 is 1, that's n plus 1. So I'm going to get n plus 1 every time. So n minus 3 plus 4 is n plus 1. And then n minus 4 plus 5 is n plus 1. And dot, 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 all the way out to n plus n. Or, let's see. Okay, we're going to end up with, stop, it's always going to be n plus 1. Okay? All right, so n plus 1 plus n plus 1 plus n plus 1 plus n plus 1, and that is going to equal the number of n plus 1s times n plus 1 times n. So that would be 2t of n is going to equal n times n plus 1. Okay, however many times n plus 1 occurs. So if it was 4, then 2t of n would be 4 times 4 plus 1, which is 4 times 5, which is 20. But there's only 10 in that one. So if I divide this now by 2, then I get my triangle of t of n equals n times n plus 1 divided by 2. So let's check that. If I used this right here, my n is 4. N plus 1 is 5. 4 plus 1 is 5. 4 times 5 is 20, divided by 2 is 10, and there's my 10. Okay. All right, so now we have it. So now it says find a formula for t of n. So there it is. Starting with n equals 1. There's our formula. Okay, it says, how can you be sure that your formula works? How can we be sure this formula works? Okay, so by substituting a term number into the formula, you get the correct number of dots in that figure. The formula also works because each triangular number is exactly half of a rectangular arrangement of dots whose dimensions are n by n plus 1, for example. Okay, so again, we could just take this one here, and our n is 5. How many are in the bottom row? It's 5. Didn't mean to move that. Okay, so it's 5, so n is 5. 5 times 6 is 30, divided by 2 is 15. In this one, the bottom row is 3. 3 times 4 is 12, divided by 2 is 6. In this one, it's 1 by 2, because 1 plus 1 is 2, which is 1 times 2, which is 2. 2 divided by 2 is 1. Okay, so the formula does work. Okay, so we want to create a graph of this triangular formula, t of x. So if I plug in 0, I can't have a side length of 0, so that makes no sense. So I'm going to start with 1. So I will put 1 right here. And this is my x-axis here, and this is my y. It's not showing the axes, but let me put it on there. Okay, so that's better. All right, so anyhow, here's 1. When I plug in 1 here, it's 1 times 1 plus 2, 1, which is 2. 1 times 2 is 2. 2 divided by 2 is 1. So I'd put the dot right there. So then when I go to 2, right here, 2 times 2 plus 1, which is 3. 2 times 3 is 6. Divided by 2 is 3. So I would go up to 3 here and put a dot. If I plug in 3, then it's 3 times 3 plus 1, which is 4. 3 times 4 is 12. Divided by 2 is 6. 1, 2, 3, 4, 5, 6. So I'll just label each fifth. There's 6 right here. All right, number 4. If I plugged in 4 here, 4 times 4 plus 1, which is 5, is 20. Divided by 2 is 10. 6, 7, 8, 9, 10 is right here. So therefore my dot would go here. All right, and then 5. 5 times 5 plus 1, which is 6. 5 times 6 is 30. Divided by 2 is 15. 1, 2, 3, 4, 5. 15 is right here. And there it is. So it's hard to tell on this, but it is growing faster. There's only we only went up 1 here, then we went up 2, then we went up 3, then we went up 4, then we went up 5, then we're obviously going to go up 6, and so on and so on. Okay, how are your two graphs alike and how are they different? What two graphs? Create a graph of the sequence, done. Create a graph of the triangle area formula T of x. Did I skip one? Something is missing in this student edition. I'm going from 11. Oh, I bet you I know what. I think I covered it with this. Whoops. Okay, just one moment. Okay, my apologies. I did T of n first. Or I did n first. Okay, so let's do this one now. Again, it's going to be, can't have 0. And if I put a 1 here, 1 times 1 plus 1, which is 2, is 2. Divided by 2 is 1. That would go here. And then when I plug in a 2, then I'd get 6 divided by 2, which is 3. And then when I plug in a 3, I'd get 3 times 4, which is 12, divided by 2, which is 6. So 2 was 2 times 3, which is 6 divided by 2, which is 3, not 2. So I've got to move this up 1. That's 3. All right. Plug in a 3. 3 times 4 is 12, divided by 2 is 6. 3, 4, 5, 6. And then 4 would be 4 times 5, which is 20. Here's my 5, 6, 7, 8, 9, 10. 20 divided by 2 is 10, so that would go here. And then 5 would be 5 times 6, which is 30, divided by 2 is 15, which is right here. Now what we need to pay attention to is the wording. It says create a graph of this sequence where n is a positive integer. So 1's an integer, 2's an integer, 3, 4, 5 are all integers. But then when I move to 13, it says where x is any positive real number. What's the difference between our graphs? Well, I can start at 0 and it's any value in between. It's very difficult for me to draw a curve here, but you get the idea. It's every value in between as well. I could do 2.5, 2.6, 2.7, 2.8. All positive real numbers do not have to be just integers. The difference is the dots are connected in this one, and wherefore these are just dots with nothing in between because they were only positive integers. Okay? 14. How are the two graphs alike? And how are they different? Well, I just explained how they're alike, or how they're different. Okay? They have values in between on this one, but not on the other one. So there's this graph, and then this graph. But the integers are the same in each graph. It's just that this graph has values in between. Okay, that is the end of lesson 8. Go do your problem set.